All right, this is the automatic card collector, shuffler, and dealer senior design project. I'm Isaiah Nolan. I'm a part of I'm assigned with the software development, material, and mechanical design. Mansour Aldanati or Alnayati is responsible for motor and actuator research and electrical development, and Suhaid uh, Haid is responsible for electrical development as well. Our project faculty advisor is Professor Hadi Elasti. Here's our high level OV1. Reading it from left to right, you can see that the LCD touchscreen, all the information from the touchscreen goes to the MCU for uh, coding and deciphering. And then also power is going from power to the MCU2, which also gets sent to the LCD touchscreen. Um, from the touchscreen, you can get card game selection. From there, you get how many users are in the game. And after that, the system comes to life, and you see card. The system deals the cards. Once the end of hand happens, there's a button that the user can press, and once the user presses that, the card collecting begins, followed by the shuffling, and then also the user will after the end of the card shuffling, the user will get an end of game uh, button that they can press. If they do press it, the game's over and the system will turn off. If not, the user will get another question asked on the touchscreen, and they will have to input the number of users again. Here's just a functional diagram. So I kind of already explained it, but the executive summary for the automatic card collector, shuffler, and dealer, what it's supposed to do is it's supposed to introduce robotic automation into the card arena. The system's hardware will include a Elegoo microcontroller, a Nexteon human-to-machine interface, or an HMI touchscreen, structural parts for the base, head, and arms, motor and actuators, suspension cables, and a gear track, a card shuffler, and a card shooter/dealer. The software for the system will be Arduino code, and that will be written on the Arduino IDE. The software will allow the user to again select the preloaded card game and the total number of players, and the touchscreen GUI will also act as a way to interface to the Elegoo. So here's some design challenges and iterations for our system. So our first couple of weeks from September 5th to the 26th, we selected our project. The initial research began in this time frame, particularly on the MCU and motors. Group roles were assigned based on personal qualifications and personal selections. Research regarding the MCU is completed around September 26th, and the Elegoo Mega R3 with the AT Mega 2560 is selected. Research regarding the touchscreen is completed, and we came to the decision to use the Nexteon enhanced 3.2-inch HMI display. And then research regarding the first table design is completed during this period too. Our next time period that we completed research in was between the October 10th and October 24th. The first design and material selection regarding the table are selected, and carbon fiber was initially chosen as our material for the table. The design for the system's card hoppers and card chutes are designed and 3D printed for testing. Testing for these was successful, and any improvements that could be made are noted. Collector arm motors are selected. We ended up selecting the Miyuze Micro Servo 9G motor. Collector arms are designed and 3D printed for testing. The testing that we did on these arms showed that they were too heavy for the motors that we had selected. So new motors were researched and selected for the shoulders. We came to the decision to use the high-tech HS 7955 TG servo motor. Our next research period was between November 7th and November 21st. Circuit design for the motor driver circuit had been completed. The motor driver circuit will allow the MCU to control any of the motors and supply adequate amount of current. The circuit design for the power supply circuit had been completed. The project will be powered using normal city power, 120 volt AC, 60 hertz city power. To avoid any tangled wires, a slip coupling will be used to connect a laptop charger to the power supply circuit. Around mid-November, November 21st, table materials changes due to price and material conflict. The price of carbon fiber would have been a couple of extra $100 compared to wood, so we made the switch based on that. And cutting carbon fiber is difficult and could expose us to dangerous particles. So that was one of the reasons. The other reason is carbon fiber is conductive, which we did not know. So if we used carbon fiber, we would have needed to insulate any wires extremely well to avoid shorts. And then from December 5th to the present day, the table legs and additional support has been cut to size. The Arduino code for the preset games has been completed. The HMI has been designed, which includes the preset games, a slider for number of players, a deal button, and an end-to-hand button. The Arduino code that registers and displays the game selected on the touchscreen has been completed, and parts for the project have been ordered, including motors, actuators, the PCBs, the PLA for 3D printed parts, and other miscellaneous parts. So for the software design process, this is what the software flowchart is. The system software needed to accomplish 3 tasks. It needed to store card games and the rules. It needed to use the number of players to control the table and dealer motors, and then it also needed to have a timing function to switch between processes. The Elegoo MCU will control the touchscreen and all the motors as well.
So now we're talking about the hardware design process. So put it simply, design processing first includes the schematic design, and then the simulation, then the hardware assembly, and then the testing and iteration. So for the schematic design, the voltage regulation circuit was designed in multi-sim, and after that, I imported it to Altiboard. And after the schematic design was done, we simulated in multi-sim and Altiboard. And after that step, which we haven't done yet, is the hardware assembly. We will assemble the components into a PCB, ensuring compact and robust wiring. Motors and gears will be aligned mechanically for efficient operation. After that's done, we're testing and iterating. Motors will be tested for speed, torque, and accuracy. Now for the circuit schematic and multi-sim. So we've designed 2 circuits. One is the voltage regulation circuit in the first diagram, and the second diagram is the motor control circuit. So the purpose of the voltage regulation circuit, it provides stable power to motors and microcontroller to ensure the hardware operates safely and consistently despite variations in the input voltage. The key components of the voltage regulation circuit is the LM317 voltage regulator U2. That the reason we use that uh, is it provides a desired output voltage by adjusting the resistor network. The LM1317 regulates the voltage down to the appropriate level for the motors and the microcontroller. And the input receives a 20 voltage power supply. And the output is a VCC, which self-explanatory delivers the regulated voltage to the rest of the circuit. And the capacitors filter out the noise and stable the voltage supply to prevent any fluctuations. And for the second circuit, the microcontroller motor controller circuit, it controls the movement of the motors to shuffle, collect, and deal the cards. The components that are used is Arduino, which Isaiah talked about, and the motor drivers, edge bridges, they act as intermediaries between the Arduino and the motor. It acts like a medium between Arduino and the motors, providing a sufficient current and enabling directional control. And obviously, the DC motors, we'll be using 4 motors, and each motor has a task. One of the motors will be for the shuffling of the cards. One of them will be for dealing using the precision roller mechanism, and 2 for the controller's arm to grab and organize the cards. And we'll be also be using the potentiometer, allowing manual adjustment of motor speed, aiding the fine tuning during testing.
For our next part, we have multi-board circuits, a schematic. So in multi-board import the multisem schematic, place power component, connector, capacitor in one corner for effect, efficient wiring. Position in the microcontroller centrally with the motor driver nearby for the short tracepad, and place encoder and sensor I/O component at the edge of for the easy access. And the route trace with the wide power trace to handle motor current, and a separated analog and digital ground plane to the reduce plane digital ground plane to the reduce noise. Keep sensors signal trace short to minimize interference. Finally, we use a design ruler checker to check for the open connection, short circuits, or clearance issue. Adjust the design as needed. And car shuffler and collector circuits included full segment, power supply section, control segment, and motor segment and feedback segment. An automatic car shuffler collector system is consistent. Four key. The first one is power section. Provide stable voltage for the system, and with DC power supply, 12 volt or 24 for motor, and a 5 volt regulated supply for the microcontroller. The high frequency decoupling capacitor ensure the clean voltage, prevent noise from affecting motor and sensor. The second one is control section, which managed by the microcontroller in control for the it control motor operation by sending PWM signal for the speeding and direction. It also received input from sensor, position sensor limited switch to adjust the motor movement, uh, doing shuffling and dealing or collecting card, ensuring synchronizing timing. The third part is motor section. It use steeper motor and driver for the precise position of the collector arm and car shuffler. The steeper motor provide accurate car placement and movement control, and their speed. Direction are adjusted by the microcontroller to ensure the smooth and jam-free operation. Finally, the feedback section include encoder and position sensor to monitor motor and car position. The microcontroller uses feedback for the real-time adjustment, ensuring proper car handling and correction any deviation in the system operation. And here we have project risk. The synchronized issue impact is and and sorry and coordinated movement can cause system breakdown. And implementing feedback systems such as sensor conduct extensive debugging. Supplier delayed. We have could delay like a project timeline, order a critical part early, and identify alternative supply. Inconsistent card handling. Car could jam or not shuffle correctly. or regular calibration tests and testing to ensure proper alignment. And we could have like MCU or motor damage, usage of capacitor for stabilization, and verify regulator circuits design and include fuse. Work to be completed. A table assemble needed to be completed. Part needed to be ordered from respective vendor. 3D printing system hardware not include the table. Igloo MCU needed to be integrated into the 3D printed part. Software testing post integration. A hardware testing post integration. A report need to be written that include technical detail of automatic car collector and shuffler dealer. A presentation needed to be created to summarize the technical report of automated car and collector and shuffler and dealer.